Imagine a highly capable robot arm, meticulously programmed to perform a task with precision and grace. Suddenly, it stiffens, unable to move in a desired direction, even though it appears perfectly capable. What just happened? This common scenario is often due to a phenomenon called a singularity. Singularities reduce a robot's degrees of freedom by forcing certain joints into a specific geometric alignment that temporarily removes the robot's ability to move its end effector in one or more directions. Essentially, the robot becomes constrained in its movement options, even if it has ample physical range remaining. The core reason for this reduction lies in the robot's kinematics, specifically how joint velocities map to end effector velocities. This relationship is mathematically described by the Jacobian matrix. When a robot enters a singular configuration, its Jacobian matrix becomes rank deficient, meaning its determinant approaches or reaches zero. This mathematical condition indicates that some of the independent axes of motion for the end effector have effectively collapsed onto each other, thereby reducing the number of unique directions the robot can instantaneously move in. For engineers and programmers, understanding how to manage these points is crucial. Identifying potential singular configurations involves analyzing the robot's kinematic model and the conditions under which the Jacobian determinant becomes zero. Trajectory planning algorithms are then designed to steer the robot's path away from these problematic zones. Sometimes, redundancy resolution techniques are employed for robots with more than 6 degrees of freedom to find alternative joint configurations that avoid singularities. It is also important to know that singularities are typically categorized into different types, such as wrist singularities, shoulder singularities, and elbow singularities, depending on which set of joints causes the alignment. Each type presents unique challenges. For example, a wrist singularity occurs when the wrist joints align, causing the end effector to lose its ability to rotate about a particular axis. The concept of a manipulability ellipsoid helps visualize how a robot's ability to move changes in different configurations, visibly shrinking or deforming at singular points. Ultimately, recognizing and mitigating singularities is not just a theoretical exercise. It is fundamental to designing robust, reliable, and efficient robotic systems. By carefully considering these kinematic limitations, we can ensure that robots operate smoothly, predictably, and safely across their entire workspace, avoiding unexpected stops or unpredictable behavior.
If you love robotics, like, subscribe, and keep building with us.